Hello students. Today in this lecture we will discuss some topics of the solid state, that is the closed packed structure, then the formula, and then the packing efficiency of the crystal. Okay, so let's begin. The packed structure of the solid state, it may be considered in all the three dimensions. So in the first dimension, close packing in one dimension, first of all we have to know one more definition which is written here: coordination number. What is this? The number of nearest neighbors of particle is called its coordination number. So if we are talking about the one dimension means when there is one axis. So before discussing all these topics in close packing, we are considering all the particles like a sphere. Clear? So if we are discussing the close packing in one dimension means one axis. So all the balls, or when I am saying it is all the spheres, it means they are the constant particles. When all the constant particles are arranged in a line or in one axis, then this kind of packing is termed as close packing in one dimension. And in the case of this kind of packing, the coordination number of each and every sphere is 2, because the neighboring sphere or neighboring constant particles which are in direct contact with each other is 2. For example, if you are talking about this constant particle, so the coordination number is 2 because the neighboring particles are only 2 in number. Clear? So this is the close packing in one dimension. Now the close packing in two dimension means when there are two axes, means if this is x axis, then y axis also. Clear? So in the case of two dimension, there are two kind of arrangement means if the particles are arranged in a ray, and the second layer of the particles or the sphere is just on above of each other, means just direct contact with each other. Clear? So this is one arrangement, and in this arrangement the coordination number of each and every constant particle is 4, because 4 atoms or constant particles are in direct contact with each other. So when you will join all these, the center of all these spheres, then you will get a square. That's why it is termed as a square close packing. Clear? Now the next kind of the close packing in two dimension is hexagonal close packing. And one more thing, in the case of square close packing, it is also termed as a type of packing. Whereas in the case of another kind of packing in two dimension, when there is a ray of the spheres, and when you are placing the another ray of the constant particles, or you can see the row of the particles, these row of the particles can be placed in the depressions of the first row appeared. Okay, so these are the depressions. Whenever next row is placed on the depression of these the first row, this next row is termed as B, because it has different arrangement from the A. And the next one is again in the depression of second row, then next one is the depression of the fourth row. So if this kind of the arrangement is there, so every alternate layers are of different arrangement. That's why they are termed as AB type of arrangement. And if you are talking about the quantum number of one sphere, then in this case there are 6 spheres which are in direct contact with each other. That's why the constant number in this case is 6. Clear? Now next one is the close packing in 3 dimension. So in the case of 3 dimension, again there are more than one structure. Before that, I will show some kind of model here, for which I prepared the ball of the flower. So because of lockdown, I am not able to collect any kind of spherical material. That's why I made it. So this is the arrangement in the case of one dimension. And the square close packing is like this: if the rows are arranged, so again this is having only one axis, means this is the one line arrangement. That's why for example it has only x axis, and it has x as well as y. If this is x axis, this is y axis. Clear? So this is square close packing. For example, if you are just taking this ball, this is sphere, then direct contact balls, number of balls, 1 2 3 and 4. That's why when you are joining these center of these balls, it will get square structure. And the second one is hexagonal close packing, in which this is the first row, and in the second row is placed in the depression of first row. So this is the depression of first row. So another row is placed like this, and again the third row is placed in the depression of second row. So this is the third row, then fourth row. So if you will observe, then this row is different from this but similar as third one, the A and B. So that's why A B arrangement. Clear? Now the third 3D dimension, in 3 dimension, when close packing in 3 dimension is studying, then these two structures which we have discussed here, square close packing and this hexagonal packing, will be considered. So in the case of square close packing, there is only one way: just place the ball on just above the another one, means in direct contact, like this. Clear? So it can be clearly appeared in this diagram. So this is one axis, one axis, and the second axis, and third axis is the height. That's why it is 3D. So how this third axis will be there? For example, if this is the arrangement in the 2D, so all when you are arranging these kind of balls above one layer, two layer, three layer, four layer, so the height will increase, and if the height will increase, it means third dimension will be appear. So in this case, the diagram will be like this. Okay, so in this case, when you are joining the centers of each and every adjacent constant sphere, or you can say the constant particles, then you will get the cubical structure. This will have the cubical structure. So it can be considered as cubic close packing. This is cubical lattice, because every sphere is considered as is having the same dimension. That's why the structure become cubical. Clear? So in the case of square close packing, when you are framing it into 3D structure, then there is only one structure. But as you are moving to the next page, where we are going to just identify what will be the arrangement in the case of hexagonal close packing, then there are some important topics. The voids. What are voids? Voids are the empty spaces present between the constant particles when they are arranged in a crystal lattice. So you are very clearly seeing here T and O. They are two letters: T for tetrahedral, O for octahedral. So what does it mean? What is T and what is O? So when you are just placing the second layer in the case of hexagonal close packing, then just focus on my lecture. When you are seeing, this is the first row. Okay, so there are two kind of the voids, or you can say there are two kind of the depression. This is apex upward, and this is apex downward. And apex upward. For example, in this, apex upward, apex downward. Clear? In this diagram also you can see apex upward and apex downward. Clear? Triangular shape structure can be drawn here. So when you are placing the second layer, there are two possibility where you have to place the next layer. So if I am placing the next layer like this, so I arranged the next layer, means when I have placed second layer, and where I have placed the second layer on the apex upward voids. What is the void? What is the nature of the void? Apex upward. So this is apex upward. So if you have placed the second layer, then again you will observe two kind of the voids are there. One is this one, which was earlier void. Earlier void means below this layer it was again void. Just see here. This was void in the first layer, first you can say the plane or the layer, and when you place the second layer, then again it remained the void. This remained the void, and the second one is this one, which was not earlier void, but in this layer it is void. Clear? Now if you are trying to just cover the void. There are two kind of the voids. So if you are covering this void, if you are covering, then what is happening? The first layer is just similar to the third layer. Just look at the model. When I am picking this ball up, so exactly below this ball the first layer is there. So this is A B A B A B A B type of arrangement. Clear? And now just look at the structure of this void. This is the void, this is the blank space, empty space. So when you are covering this void is termed as tetrahedral void. Why it is tetrahedral I will discuss later. But if you are just looking at this void, the coordination number of this void, not the coordination number of the constituent particle, I am talking about the coordination number of this void. Void means empty space. So empty space of this void is how much? 4. Is that clear? Why this is 4? Because this void is surrounded by 3 particles here and 1 is above. So total number of particles or constant particles which are covering this void is 4. That's why the quantum number of this void is 4. Clear? Now if this is the first way of covering the voids, so this arrangement is A B A B A B type of arrangement, and when you will just go through the book, then you will clearly observe that arrangement is termed as hexagonal close packing in 3D structure. Clear? But there is one more kind of arrangement where third layer can be placed on this void, so the structure become completely different. Means this third layer is completely different from the first one. So this means the first layer is termed as A, the second is termed as B, and third is termed as C layer. This is arranged, this is termed as A B C, then the fourth layer will be A B C type of arrangement. Clear? Now the nature of this void is the void here, because it was earlier void in the case of first layer, and again in the case of second layer it was void. Clear? So if you are covering this void, then in this case the void is termed as octahedral void. Why it is octahedral? Because it has 8 faces. But when you are talking about the coordination number, then what is the coordination number of this void is? It is 6, because as I am removing the ball, just count it. First ball, second ball, third ball, and three more. 1 2 3 means total 6 balls are here. 6 balls means 6 constituent particles are there, means the quantum number of this void is 6. So in the case of octahedral void, the quantum number is 6. Clear? And how this structure will be obtained? So 3 balls like this and 3 balls like this. So when you will draw it like apex downward and 3 apex upward. So when you will join the lines, then what will be the structure? It is octahedral. Why it is octahedral? Because it has 8 faces. 8 faces. How it is 8 faces? 1 2 3 and 4 behind it. 4 above the plane and 4 below the plane. Total 8 number of faces. That's why it is termed as octahedral, 8 faces. And in the case of tetrahedral, which is written here as O and T, O for octahedral and T for tetrahedral. So whenever you will go through the book, you can clearly just conclude it. So how this tetrahedral void is there? So 3 balls are here and 1 ball is just placing above it. So this is the tetrahedral hole. By chance, in the case of tetrahedral void, the number of constants phase 4 as well as the number of faces is also 4. So you don't have to confuse in the name tetrahedron and octahedron. Tetrahedron is because it is having 4 faces, and octahedron means it is having 8 faces. It doesn't mean that they are having the same number of coordination number also, By chance, in the case of tetrahedral, the coordination number is same, it is 4, but in the case of octahedral, the coordination number is 6 only. Clear? Now when just you will just observe this kind of arrangement, AB type of arrangement, when you are covering all the tetrahedral whites, which I have already shown you. And in the case of when you are covering the octahedral white, then it is ABC type of arrangement. So when AB type of arrangement is there, it is termed as hexagonal close packing. And when you are observing as ABC type of ABC type of ABC type of arrangement, then it is the now the number of coordination sphere. What are the number of coordination sphere? Number of coordination sphere in the case of both the hexagonal close packing and cubic close packing is 12, which is written at the topmost here. The coordination number is 12. Clear? Now I am going to just tell one more thing. The number of octahedral whites and tetrahedral whites. If the number of spheres in the closed package structure is n, then the octahedral whites are also it is equal to n, and tetrahedral whites are 2n. How will this can be proved? So it is very easy. Now in next page it is clearly mentioned in these two diagrams. So in this diagram we will discuss the structure of the FCC arrangement. FCC arrangement is just similar to cubic close packing. Clearly, so in the case of FCC means face centered arrangement. Face centered arrangement means they are the corners which are occupied by the spheres, and at the center of the all faces they are the sphere. So all the red balls which are appearing in this structure is the constituent particles. So these are the corners and these are the face center. Clear? So how this tetrahedral wide is just 2n, it is very clear. Now tetrahedral arrangement is the arrangement when there is the constituent particle, then empty space, then constant particle, then empty space, then constant particle, then empty space, and then constant particles. Means if 8 corners are there and you are just arranging alternately, means particle, empty, particle, empty, particle, empty, particle. Clear? So this is the arrangement in which you can see 1, 2, 3 balls and 4 balls. Ball means the constant particles only. So it is a tetrahedral structure. It is tetrahedral structure, and the coordination sphere is 4. 1, 2, 3 and 4. So the void present here, void means empty space present here, is surrounded by 4 particles. Clear? So this is the void present here in this portion is tetrahedral void. So and this is one small portion, small cube. So total number of cubes in it is 8. 1, 2, 3 and 4 and 4 above. Total number of cubes in this structure is 8, and if this number of cubes are here 8, then total number of tetrahedral void is again 8. Clear? Now what type of structure is it? It is face centered, and in earlier lecture we have discussed in the case of FCC arrangement how many particles are there? 4. So if 4 particles are there in the FCC arrangement, then according to the concept, how many tetrahedral voids should be there? It is twice in number, that is 8. Clear? So this is the concept behind why tetrahedral voids are twice in number. And the next is the octahedral void. Octahedral void is just equal to the number of particles present. So again FCC arrangement is there. Octahedral means the coordination sphere is 6. So just look at the center of this whole structure is a kind of void, and it is surrounded by 6 face center. 1, 2, 3, 4, 5, 6. So this is one void which is present at the center. And where are the other one? Just look at this structure. This is the edge of the cube. At the edge of the cube there is an empty space which is considered as octahedral void. Why it is void? Because the quotient number is 6. How it is 6? This sphere, this sphere, this sphere and this sphere, it is present in this cube only. But along with this cube there are so many cubes which are in surrounding. So from this side one sphere, this side one sphere, means from at each edge there is a void which is surrounded by 6 constituent particles. Clear? So this is also a kind of octahedral void. It is clear or not? Because the number of particles which is surrounding this void is 6, 1 and 2, then 4 on the plane. Clear? So this is the octahedral void, and this void is present at the edge of the cube. So how many edges are there? There are total 12 edges. 1, 2, total 12 edges are there. Clear? Any confusion? Total 12 edges are there. And all the edges are shared by 4 cubes. 4 cubes are sharing all the edges. So when you are solving it, then how many number of particles, or sorry, how many number of voids can be occupied in the case of one cube? It is 3 in the from the edges and 1 from the center. Total number of void is 4. Total number of void is 4. It means, and in the case of FCC, what is the number of particle? It is also 4. So void is 4 and number of particle is 4. Clear? So on this basis you can conclude that the octahedral void is just exactly equal to the number of particles present in the cube, and the tetrahedral void is just twice in number. Clear? Our next topic is the formula of a compound and number of voids filled. It is very simple and nothing very difficult. For example, this is the question. A compound is formed by two elements X and Y. Atoms of the element Y make CCP, and those of the element X occupy all the octahedral void. What is the formula of the compound? Very simple. Whenever there is a question, and in the question what is there? Atoms of the elements Y make CCP. So let the number of Y is, for example, A. Clear? Then, and those of element X occupy all the octahedral voids, all the octahedral voids. So if the number of particle is A, therefore number of octahedral void is equal to also A, according to that concept, and therefore the number of X particle is also A. Why it is A? Because it is written here, the element X occupy all the octahedral voids. Therefore the ratio of X and Y is A is to A, means 1 is to n. Therefore formula is X and Y. Clear? Similarly, in the next question, the atoms of element B from SCP lattice and those of element A occupy 2/3 of the tetrahedral voids. What is the formula of the compound? So element element B form SCP lattice. Therefore let the number of B is A, or you can say here X. Therefore the number of tetrahedral void is 2x, because it is twice in number. And what about A? A occupy 2/3 of tetrahedral voids. So the number of A particle is 2/3 of tetrahedral voids. It is 4x by 3. So the ratio of A and B, A is 4/3x and B is x. When you are solving it, it is 4 is to 3. Therefore A 4 and B 3. This is the answer. Clear? So this is all about the formula, how you will draw the formula. The next is the packing efficiency. It is very easy. Packing efficiency in the case of SCP, CCP and FCC. FCC is also having the same packing efficiency. It is very simple. FCC means at the corner and at the face center. So in this in the textbook it is very clearly mentioned, this is the right angle triangle, and apply the Pythagoras theorem. And after applying this Pythagoras concept, the overall efficiency is 74% in the case of FCC. And in the case of body centered arrangement, so body centered arrangement means at the center of the body, means these are the corners and this is the body center. So when you will join, this is also a kind of right angle triangle. So in this case, there are two right angle triangle for calculating this. One is this one, and another is this one, because you have to calculate this b. So for b you have to solve this one also. Clear? So when you will solve this packing efficiency in the case of body centered, it will come as 68%. Clear? So the efficiency of FCC is 74%, efficiency of BCC is 68%, which is quite low on the FCC. And the next one is simple cubic, packing efficiency of simple cubic lattice. Simple cubic lattice means only there is the arrangement at the corner of the cube. So it is very simple. And all these three in these three discussion, the edge length is considered as a, and the radius of the particle is considered is r, small r. On this basis the calculation is 52.4. It is very low. So when the question will be asked, it is very clearly concluded here that the packing efficiency of simple cubic crystal is very low. It is 52.4. Thank you.